capacitor is a vital device that stores electrical energy and is widely used in electrical circuits for various types of functions. When purchased new, positive end is normally longer and the negative end can be taken from the marking given on the cover. Shown below are high-voltage ceramic capacitors with 15,000 volts. When handling capacitors, need to be very careful since these charged capacitors can release high voltage and current within fraction of a second. On the right side, you will see a normal capacitor used in motors with markings of 25 microfarads, plus or minus 5% and 450 volts AC. 25 microfarads, with plus or minus 5% means that this capacitor can handle in the range of 24 to 26 microfarads, since 5% of 25 is only 1.25 microfarads. 450 volts AC means that it is the maximum voltage this capacitor can handle, but it can be used to replace any capacitor with a given voltage less than this maximum value. This can be used for 380 volts or 400 volts marked on a capacitor, but not on a 455 volts marked on it. Parallel plate capacitor is the basic capacitor, where you can understand the function of it easily. Normally, two metal plates kept parallel to each other and a dielectric or non-conductive insulated material thin layer is uniformly laid in between the two plates in a simple parallel plate capacitor. If you remove the cover on it, you will see inside like this. Positive and negative connections marked here and the two metal plates with the thin dielectric in between two can be seen. Now let's connect a battery to the capacitor, and the positive and negative sides also marked here. Thin dielectric is widened here to show the function properly. Two plates also widened and you will see how the electrons with negative charge bond with the positive charge to make them neutralized. Molecules in non-conductive dielectric too are with negative and positive charge, but spread irregularly since zero influence from neutralized molecules of conductive plates. When switch is closed, electrons start to flow from the top plate to positive side of the battery, and electrons from negative side of the battery continue to flow to the bottom plate and accumulate there. Normally current takes opposite path of the electrons, that is from positive to the negative. But here dielectric does not allow any current to flow through it. Electrons flow will continue till the voltage between plates become equal to the voltage difference of the battery. Since the neutralized molecules do not affect the charge on plates, those can be removed now. When neutralized charge had been ignored, there will be positive charge on top plate and negative charge on the bottom plate. Previous irregular pattern on molecules of dielectric too will be changed to an organized pattern now. Positive side of the plate attracts negative side of the molecules, and the pattern continues like this. Conductive plates on top and bottom hold equal and opposite charge between its surfaces, thus developing an electric field within the dielectric material. Although an electric field develops inside of the dielectric, it will never allow any current to flow through it as explained earlier, but holds a good charge in between the plates. Capacitor is charged now, and has the same voltage difference between the two plates as at the battery. Even if you remove the battery now, capacitor is with its stored charge between the plates. Now we will connect a bulb to the charged capacitor. When the bulb is connected to it, electrons start flowing from the negative end of the capacitor to the positive end and neutralize the positive charges on it. Electric field between plates inside of the dielectric disappears, and the voltage difference too falls back to zero. Brightness of the bulb also becomes dim up to the zero level. This happens till the capacitor is fully discharged. Fully discharged capacitor will remain in neutralized state till it will be recharged again. Let's see how the capacitance of a capacitor is defined. On the capacitor, we will mark V as voltage across the capacitor. Thickness of the dielectric as simple d. Q as stored charge measured in coulombs. And the electric field measured in volts per meter. Unit measuring the capacitance is given as farad. Since farad is comparatively large unit, We normally take microfarad value or even smaller units to show capacitance on an actual capacitor for easy reference. For an example, 25 microfarad is 25 multiplied by 10 to the power minus 6 farad or 0.000025 farad. Then the capacitance can be given by the equation capacitance equals stored charge on it divided by voltage across the capacitor. If you know the stored charge of a capacitor in coulombs, divide it by the voltage across the capacitor to get the capacitance in farads. Further, capacitance can be taken by physical means of the used material, and you need to know about the permittivity then. Permittivity is commonly symbolized by the Greek letter epsilon. Permittivity is the ability to polarize through the dielectric, or simply, how much polarization is being permitted through it. It differs from material to material and the unit is measured by farad per meter. Then the capacitance equals permittivity of dielectric multiplied by the square area of metal plates divided by thickness of dielectric. If you know the square area of the two plates in square meters, and both permittivity and the thickness of the dielectric, then capacitance in farads can be calculated from the given equation. Further, electric field inside the dielectric can be derived from the equation electric field equals voltage across the capacitor divided by thickness of the dielectric. Hope you got fair amount of knowledge on capacitors and how it function. If you think that this video is useful, please subscribe to the channel. Thank you.